We now have a mathematical way to describe the position of a star in the celestial sphere. So we know where it is in the sky. What we need to do to finish our project is to figure out how to relate where a star is in the sky to where on Earth it's visible at what time. And so let's understand exactly what this translation process is so we can make our next move. The challenge that we have to meet is explained in this simulation. Here we have the celestial sphere again surrounding the Earth. The stars are fixed on the celestial sphere. We've equipped the celestial sphere with its equator and its prime meridian so that we can tell positions of a star relative to these coordinates. And then we have an observer here at some point on Earth. We want to understand what it is that the observer sees at any given instant as the whole thing rotates. And what the observer sees is the half of the sky that is above his horizon. So his horizon is this circle here, which is an extension of the plane of the Earth near where the observer is to meet the celestial sphere. And this point over here is the point that he looks straight up above over his head, will be his zenith. And so the observer's point of view is given by this diagram, extending his horizon and then rotating to make the observer vertical. To describe where a star is, he will describe how high it is above his horizon. That's called the star's altitude. Here's a star at an altitude of 30 degrees, and here's a star at an altitude of 43 degrees. And very often we will express the same aspect of a star's position in the sky by giving instead its angular distance from the zenith. This is called the zenith angle, which is simply 90 degrees minus altitude. Once you've given either the altitude or the zenith angle, you've parameterized essentially a line of constant latitude, and we need an analog of longitude. We measure local longitude away from a particular meridian. The meridian we use is the one line in the sky that starts at our northern horizon, goes through our zenith, and intersects the horizon due south of us. So this is your local meridian. It splits the sky into an eastern half and a western half. And to designate the position of a star, we measure its angular distance from this meridian, moving to the east, so that a star that is due east will be at azimuth 90 degrees, and then various altitudes. This is how we describe to someone which way they need to look to find a star. Summarizing again our coordinates in our local view, we measure the position of a star by giving either its altitude above the horizon or its angular distance from the zenith. These two add up to 90 degrees, and its azimuth, the angle from north, measuring east from 0 to 360 degrees. And then we add our special points. The zenith, the point directly overhead, at altitude equal 90 degrees, or zenith angle equal to 0 degrees, and the zenith has no azimuth in the same way that the North Pole has no well-defined longitude. We have the horizon, the collection of all the points at altitude equals 0 degrees, or zenith angle equal 90 degrees. And then we had the local meridian, the line that divides the sky into an eastern and a western half. This is the line that meets the horizon in both the north and the southern points. And so these are all the points with azimuth equal 0 degrees for the northern half from the northern horizon to the zenith, or 180 degrees for the part from the southern horizon to the zenith. That is the local meridian. These are all the stars that are neither east nor west of us. Now, what we need to understand is how to translate positions on the celestial sphere in the celestial sphere coordinates to positions in the sky in this altitude and azimuth coordinate system. And so here we have our little Earth inside a large celestial sphere. Remember, the celestial sphere should be huge. We have the poles of the celestial sphere here. We have the celestial equator over here, and two diameters drawn for convenience. And so we will place our observer over here at some particular latitude, and this observer will come with a horizon, a half of the sky that he is able to see, and we've drawn this before. This is the line. Notice that it should go through the center of the celestial sphere because the celestial sphere is so large, and therefore this is the visible half of the sky. This is the two-dimensional version of what we did before in 3 dimensions, and what this makes clear is if you look at the geometry for a moment, then this angle determining the latitude, the angle between this diameter and this line, well, this line is vertical, so perpendicular to the horizon. These two diameters have a 90-degree angle between them. The net result is that this angle here is also the observer's latitude, which means, remembering that this is the horizon, that your latitude is the angle from the horizon to whichever celestial pole is visible. In other words, if you can find the North Star or the South Celestial Pole in your sky, you now know which direction is north or south, depending which hemisphere you're in, and you also know your latitude, because the higher your latitude, the higher the pole is in the sky. Clearly, if you're at the pole, then your latitude is 90 and the pole is directly overhead. So you can use some understanding of the stars to figure out where you are and in what direction you're going. Stars are very useful for navigation. The other thing that this diagram shows us is that if this observer looks directly overhead, he finds his zenith, and his zenith is over here. And what this shows us is that his zenith is at any given time going to be at a declination, a distance from the celestial equator, also equal to his latitude. And then as the Earth or the celestial sphere rotates, he will see different points on this line of fixed declination directly overhead. So the only points that are directly overhead ever for a given observer are the points whose declination is equal to your latitude. Here we have our favorite view of the sky in Athens again, and in addition to the green celestial grid that I drew before, centered on the North Celestial Pole, I've drawn in red our local altitude and azimuth grid, and so we see our zenith directly overhead. We see lines of constant altitude in concentric circles around it, and we see lines of constant azimuth. And as you see, we are looking due south at the moment, and so this is our prime meridian, the line that splits the sky into an eastern half over here and a western half over there. And because the prime meridian goes through both the zenith and whichever celestial pole is visible, because it, in this case, reaches the northern horizon, it coincides with some specific celestial meridian for its long part, for the part including the zenith. At this point, I think that I can tell that because this is 0-hour celestial meridian, this is the 2-hour celestial meridian, our local meridian corresponds with the celestial meridian for 1 hour. And when I allow time to elapse, then as we saw, the green grid on which the stars are fixed will move from east to west, rotating about the celestial pole. The red grid, which is fixed to us, will appear to us to be stationary. So as time goes by, the celestial lines of celestial meridians will move to the east, and whereas the lines of fixed azimuth will not, so that if our local meridian corresponded previously to the meridian for 1 hour of right ascension, now we have 2 hours of right ascension overhead, 3 hours, and so on and so forth. This animation is truly wonderful. We have here the two views simultaneously and synchronously. So here we have our observer. I've put him in the vicinity of Athens, Greece. We see the celestial sphere, inside it the Earth with an observer position located upon it, and as time goes by, the Earth will rotate inside the celestial sphere. Here, simultaneously, is the local view of the observer. We see his horizon, his northern horizon over here, and this is the half of the sky that the observer will see. And as we begin our animation, I've also drawn a few star patterns on the celestial sphere. We see here the Big Dipper near the North Pole, Orion near the equator, and near the southern celestial pole, the Southern Cross. And as our animation begins, note that if the observer looks to the east, Orion is just rising above his eastern horizon, as it was exactly in our animation, in our simulation, and now Orion will rise high in the sky, cross his meridian, and set in the west, and this will happen as the celestial sphere rotates about the observer, or as the Earth rotates, and we see Orion rising and setting. On the other hand, if we look at the motion of the Big Dipper, we notice that as the Big Dipper moves or as the Earth rotates, the Big Dipper's circle around the pole essentially never carries it below the horizon. It performs circular motion around the pole, and it never ever sets, and so that makes the Big Dipper part of what we call the circumpolar star. So there's a whole region around the pole for each observer of stars that, as the celestial sphere rotates or as the Earth rotates, never set below the horizon. And correspondingly, if you look at the Southern Cross, you see that our observer in Athens will never be able to see it. It will never actually rise above his horizon. So there's a similar region around the opposite pole that never rises. And so these stars are never visible, these stars are always visible, and then the stars in between rise in the east and set in the west. And it is this relation of the two systems of coordinates that we need to understand. Repeating, as the sky rotates above the visible celestial pole, stars close to whatever pole you can see never set, stars near the opposite pole never rise, and stars in between, or near the equator, rise in the east, move west across the sky, set in the west. Of course, for example, if you're at the North Pole, then you have half of the sky that is circumpolar and never sets, half that never rises, and stars can't rise in the east, and therefore at the North Pole, their trajectories are just horizontal circles parallel to the horizon. And we see this in these collection of beautiful images. The two images on the left are star trails. In other words, somebody left the shutter open around the south celestial pole on the left and the north celestial pole on the right. So the stars in this image would have been moving counterclockwise, and the stars in this image would have been moving clockwise. And then on the left, we see a beautiful image of star trails near the horizon. This is Orion rising, and you can see from the fact that Orion is rising and moving to the left, you should be able to figure out that this means this image was taken in the southern hemisphere. And indeed, if you're a northern hemisphere denizen like me and you look at Orion, he seems to be doing a headstand. This is because in the southern hemisphere, one's head is pointing in a different direction in space. And so we have the beginnings of an understanding of what it is that we see at any given place, and we're almost ready to make the calculation. And so the thing that we need is this description of the zenith. So I already described to you that our zenith at any point is a point on the celestial sphere whose declination is equal to our latitude. Now, over the course of a 24-hour rotation of the celestial sphere, which point along that celestial parallel we see changes. You see all of the stars over a 24-hour period which have that declination pass overhead. And so what we're going to do is, at any given instant, we can look which celestial meridian contains our zenith. And we can look at the right ascension of the celestial meridian and call that our local sidereal time. And this will, of course, change with time as the celestial sphere rotates to the east or to the west, or the Earth rotates to the east. Either way, your sidereal time will increase by about an hour each hour, and a complete rotation of the Earth, or equivalently of the celestial sphere, will advance your sidereal time by 24 hours. So sidereal time is the name of the celestial meridian which coincides with the local meridian, the one that includes our zenith. And of course, over 24 sidereal hours, when this right ascension advances by 24 hours, this is one full rotation of the Earth. So we can use the stars to measure time. The motion of the stars across the sky is a way to measure time. And indeed, in one sidereal hour, the celestial sphere shifts by 1 hour of right ascension, one parallel giving way to the parallel moved by another hour. And until the 20th century, this was in fact the definition of our units of time. A second was defined in terms of the rate at which the Earth rotates. This is a pretty stately and fixed rate, and it's no coincidence that until the 19th century, this was the most precise way to measure time that we had at our disposal. Thing to note, of course, is that different locations on Earth will measure different sidereal times, because depending on your longitude, you will see overhead different celestial meridians, and as you move to the east, you will see later and later sidereal time, because moving to the east, you see stars overhead that are farther and farther to the east along the celestial sphere, and so 15 degrees of longitude east advances your sidereal time by an hour, but this varies continuously, so that moving east by 20 meters changes your sidereal time by some small amount. Returning to our view of Athens, we can now read off the sidereal time in our picture. Remember, the sidereal time is the time indicated by the celestial meridian that coincides with our local meridian, and we've seen that before. This is the 1 hour meridian, so the sidereal time in Athens at 9 p.m. on November 27th was 1 a.m., and of course, as we allow time to progress by an hour, sidereal time will progress. We can see that by allowing time to progress, and an hour later, it is 10:01, the sidereal time is changed, it's now 2 hours sidereal time. Now, we can use this, now that we understand the position of our zenith and the location of our local meridian, we can use this to find a particular star. So let's suppose that at 9 p.m. we wanted to find a particular star. Let's imagine that we wanted to find in the sky this particular star, Alpheratz, in the constellation Pegasus. So if you look, Alpheratz, you can look it up, has celestial coordinates. It has a declination of about 30 degrees and a right ascension of about 0 hours. It lies at the intersection of this line of declination and the prime celestial meridian. That means that Alpheratz will rise in our east, become as high overhead as it's going to get when it's on our local meridian, and then start setting in the west. So the best time to view Alpheratz, in fact, is when it is directly overhead. Because it is on the prime celestial meridian, best time to have viewed Alpheratz would have been at 0 hours, at sidereal midnight, which means at 9 p.m. we're an hour too late. But that's okay. We can fix this. We can just, through the wonders of technology, go and observe Alpheratz at 8 p.m. Here we can move time backwards. And indeed, as advertised, as at 8 p.m., Alpheratz is right on our celestial meridian. It has risen as high as it's going to rise and has not yet begun to set. So at that time, 8 p.m., or more importantly, midnight sidereal time, Alpheratz will be on our local meridian. Where will it be along the local meridian? Well, this is where Alpheratz's declination comes into play. Alpheratz is at a declination of 30 degrees. Our zenith, we said, because we are in Athens, is always at a declination of about 37 degrees. This means that the angle, the zenith angle of Alpheratz, the distance between Alpheratz and our zenith at its meridian crossing at the time when Alpheratz is as high in the sky as it gets, well, its zenith angle is given by our latitude minus its declination, in general, the absolute value of this, which in our case is about 38 minus 30, or 8 degrees. So Alpheratz will attain a minimal zenith angle of 8 degrees, or a maximal altitude of 82 degrees above the horizon, quite high. Now, this tells us almost where it is. This defines it to within a circle, but because it's on our local meridian, it can only be either north or south of the zenith, and because the declination of Alpheratz is less than our latitude, our zenith is at 38 degrees, Alpheratz only at 30 degrees of declination, its azimuth will be 180, it'll be due south of our zenith at the time that it is as high as it can get. And so if we observe Alpheratz at sidereal midnight, we know exactly where to find it. And now if we need to observe Alpheratz later or earlier, we simply use the fact that we understand that over time the sky rotates about the celestial pole at the rate of 15 degrees an hour, so that if we wait an hour, and we indeed are observing at 9 p.m., Alpheratz will have moved 15 degrees to the next celestial meridian, and indeed that is what we will observe. So we have a way of finding the approximate position of a star over the course of the night. Notice that there is an explicit formula that gives you altitude and azimuth as a function of sidereal time and declination and right ascension. The formula involves trigonometry, so we won't apply it. What I want us to understand is the principle from which it's derived. So, we've achieved what we wanted. We did not complete the mathematics because it would involve trigonometry, but I think we have the idea. We know, given the sidereal time and our latitude, how to figure out where in the sky the pole is, which line of right ascension is directly overhead, and then moving east or west, we count an hour per 15 degrees, and we can find where the rest of the sky is. So we have an understanding of which part of the sky will be visible to us at any given time at a given position on Earth. We've essentially solved the problem. The one missing ingredient is that we still need to figure out what this sidereal time thing is, because our watches do not measure sidereal time. It was 1 a.m. sidereal in Athens when it was 9 p.m. on November 27th. If we could get the translation right, we'd be set. So that's the next thing we have to take on.